Welcome to week 3, part 2 of DeepRob. Today's lecture is going to be on linear classifiers, and we'll get right into it with just a few administrative updates. So in terms of the project 0 is due tonight at midnight. You should submit through the autograder. If you're having trouble accessing the autograder, just make sure you follow the link to the autograder that's in the project instructions. So at the under the projects page of DeepRob and then project 0. Everyone gets 1 extra late day token that you could use throughout the rest of the semester. So instead of having 2 late days, you have 3 now. And the way those work is it gives you an extra 24-hour window that you can make 2 submissions to the autograder without any penalty to the final project grade. A few suggestions for project 0. If you're developing locally, just make sure that you're using PyTorch version 1.13.0 because this is what the autograder is using. And then two common pitfalls that students have been running into so far. The first is make sure that you check locally that the notebook file you're saving has the outputs that you expect it to have. There seems to be a bit of a lag in the Google Drive file system, likely because it's a distributed file system between when you try to save the file versus when the update gets reflected in the GUI of Google Drive. So just make sure that you check it before you submit to the autograder if you don't want to lose out on one of your submissions for that day. The second thing that seems to be pretty common of tripping people up is either adding cells to the notebook or adding print statements within the cells. If you make any changes to the notebook file apart from just running the cells as they're given to you, make sure you remove those before your final submission. So remove your print statements or remove the added cells. So with that then, project 1 is going to be released sometime late tonight or tomorrow morning. This project is going to be covering our first machine learning models that we'll implement. So we're going to implement k-nearest neighbors, which we talked about this past Tuesday, and also a linear SVM model, which will be the subject of today's lecture. The instructions and the code for this project will be released on the project website. So take a look for that, or if you come to discussion, I'll have a link to it in the discussion notes for tomorrow. One final plug this semester for the discussion forum. If you haven't joined, if you fill out the Google form that's linked on the slides that are posted, and also the link exists on our syllabus on the website. Right now, about half of the students in the class have enrolled in the forum, and there's been a lot of good questions. Okay, so then I think this is the last administrative slide. In terms of how Gradescope quizzes will work for the semester, don't worry if you're not officially in the Gradescope course yet. The roster has still been in flux, so we haven't uploaded the final roster to Gradescope. But starting next week, we'll start having quizzes. And the way that the quizzes will work is at the start and the end of each lecture, when there is a quiz, we'll post a link that everyone who's in the class will be able to get to. Once you open the quiz, you'll have 15 minutes to complete it. They're intended to really only take probably on the order of 5 to 7 minutes. So it's going to be like 1 or 2 short questions. And you'll have a total time of 3 hours from the start of lecture till 6 p.m. When you could choose to open and take the quiz. So you don't have to take it during lecture. You could take it after if you'd prefer. In terms of what will be covered, it'll cover material from previous lectures, not including the quiz day, and graded projects up to that point. Okay. I guess I had one note on enrollment. If you're on the wait list still, just come and talk to me after the course today, and we'll figure out how to get you in the class. Okay, so with those administrative updates out of the way, now let's get kind of into the core of today's lecture. So just as a bit of a recap, you'll recall that in Tuesday's lecture from a couple days ago, we looked at image classification, and we were introduced to this core computer vision task that we want our robots to be able to perform so that they can detect what objects are in the images that their sensors provide them, so that then the robots could start to act on the environment and carry out tasks for us. So the goal within image classification, you'll recall, is we're given some input image, so this grid of numbers, and we want to then output some discrete class label that corresponds to what the primary subject is within the image. So we saw how there were a number of challenges that this task provides our computing systems. Right? So we had viewpoint variation. There was the large semantic gap in going from like a grid of integers into some high-level semantic information, like a category label. There was illumination change that we want our robots to be able to overcome, intra-class variation, and a number of other challenges that we're going to try and solve. And so the approach, broadly speaking, that this class is going to use to solve those challenges is a machine learning approach. So the core of the machine learning approach is to collect a large data set in the case of image classification, it's going to be a data set of images and corresponding category labels. We're then going to use that data to train a machine learning model, and then finally evaluate that model on new images, or potentially deploy that model on a robot that would then be wanting to classify new images. And so the two kind of core functions for our machine learning algorithms is going to be first a training function where we try to use the data to implement the model, and then finally a prediction function, which is what would be running on the robot once it's out in the wild. And so with that, in the past lecture, we looked at k-nearest neighbors as one machine learning approach that we could potentially use for image classification. And the subject of today's lecture is going to be on linear classifiers, which is building up towards the deep learning networks that we'll be looking at in future weeks. So linear classifiers, really, you can think about as being a building block of more complex neural network architectures. So the core kind of mathematical principles that we'll talk about in today's lecture are going to carry forward in all of the future algorithms that we're looking at. So in terms of building an intuition, it's very helpful to start with simple algorithms and simple models, and then work up to more complex models, because generally speaking, the intuition that you'll build in Project 1, for example, will carry forward as we look at detection algorithms and pose estimation algorithms, or on the final project where you look at a broad class of state-of-the-art deep learning approaches. So we're going to be looking at Project 1 on this. We're going to be using this props data set for our classification task. And this is similar to the SciFar 10 data set, which we talked about. The main distinction is that this data set focuses on household objects that we would like our robots to actually act on, as opposed to natural objects or like cats and dogs. And so in this data set, so what you'll find when you start working on it in Project 1 is there will be like coffee cans. So like the first row, that MasterChef can is a brand, I think it's a made-up brand, but a coffee can, like a Cheez-It box, sugar box. So these are common objects that you'd expect to see in a kitchen environment. And in total, there's going to be 10 categories that we want our classifier to try and detect, where each image within the data set is a 32 by 32 color image. And in total, the size of the props data set is the same as SciFar 10. So we have 50,000 training images, and we'll have 10,000 test images to build up our models. And so the approach for, if you're online, if you could go ahead and mute, that would be great. So the approach that linear models are going to be kind of based on is what we call a parametric approach. So the goal of the parametric approach is going to be to take in some image and to define our classifier as a function. So here on the slide, the function in the center of the screen, this function f, it takes in the image x. So this function is going to take in an image x, and then it's going to take in this parameter matrix w, which is going to hopefully produce a function that will output some 10 numbers giving a score for each of the possible classes that the input image could potentially correspond to. And so our linear classifier then is going to treat this parametric approach as a linear function. So what we're going to do is we're going to treat this set of parameters w as a two-dimensional matrix, and then treat our image as just a vector of numbers, so that the resulting function, this linear function, is just a matrix vector multiplication. Within this parametric approach, so the idea with a linear classifier is we're going to use the parameters to represent a linear function. So we have this two-dimensional matrix W, which is the weights we could think about of our model. So in order to get 10 numbers for like one number score for each of the 10 possible classes, this weight matrix is going to take on size 10 by 3072. So the 3072 corresponds to the total number of pixels in our image. So if we take this two-dimensional matrix W and we do a matrix vector multiplication with the image input, where the image is represented just as a vector of 3072 numbers, the output that our function is going to be producing is a vector of length 10, where we can interpret the 10 numbers that it produces as representing the scores, one for each class. In addition to that, one thing that's typically done is to add a bias term to give our model a little bit more flexibility in the scores that it can represent. And so to make this a little bit more concrete, it's useful to think about this in sort of a slightly simpler terms, and to actually explicitly write out what the math would be to start building up our intuition and think about how we would actually go about implementing this with our PyTorch tensors, which we're now familiar with. So let's consider an example of this linear parametric approach where we're going to take a simpler image. So let's say that we have this image of the cracker box from our data set, the Cheez-It box. But instead of representing it as that really large array of 3072 numbers, we'll just represent it as a 2 by 2 grid of pixels. So the values of the pixels you can see are these kind of hypothetical pixels are overlaid on the full-size image here. And the overall process then, we're going to start to sort of actually represent graphically. So the first operation that our linear model is going to do is we're going to take the 2D grid of image pixels and just represent it as a column vector. So all we're doing is taking the square matrix and just flattening it into a column vector. So the same 4 numbers then are shown in this column vector. So building up then, the overall function that we're wanting to implement is this matrix vector multiplication, where we take, let's say, these are just some chosen, this sort of like randomly, let's say, initialized weight matrix that we have here, W. If you take the matrix vector multiplication with our input image and then add these bias terms, it produces then, let's say, 3 scores as output if we were wanting to maybe detect or classify between the cracker box, the mug, and the sugar box in our data set. And so if you work out the math on this slide, you'll see that the output scores that we produce here are exactly the result of this linear equation. And so as we go through these slides, one thing that'll be useful is to start to think about from the tensor math that you started to work with in Project Zero, how it is you could replicate what you're seeing on the slides in the code with PyTorch, because that's what Project One is really going to be focused on. Okay, so given this math, one thing that we will probably want to do is start to build some intuition about how our model will perform. Because if you start to build some intuition about what your model is doing and how it is producing the scores that it's producing, that might give you some insight into how you could make your model better, or how you might want to change your model in the future to maybe make it more efficient or more accurate and so forth. So the first approach that we can try and take to build some intuition about the linear classifier that we have here is to think about this function from the algebraic viewpoint. So one way that we can think about that is first there's this phenomenon known as the bias trick, where we can actually represent the overall function, that w times x plus b, as just a single matrix multiply if we append just a 1 value, like a constant value of 1, to the very end of our input vector, and then add the bias terms, which we were previously adding at the very end, as just an additional column on our matrix. The reason that this is kind of useful is just from the standpoint that it can make your implementations a little bit simpler. So if you have like an optimized matrix multiply, it can somehow, like, this can sometimes help you with like slight performance improvements. When we move on to convolutional neural networks, we probably won't see this bias trick used as much, but it's just sort of it's a nice sort of algebraic result of the parametric approach with a linear classifier that we've defined. So in addition to that, so also considering from the algebraic viewpoint, because our predictions are linear, right? This is a linear function. If we ignore the bias term, there's this result, which is that for a linear function, if you multiply the input of a linear function by a constant, the output is effectively multiplied by that constant if you were instead to give it the original input not multiplied. So to make that kind of more concrete, let's say that we have our original input x and we pass it through our linear function, which is just going to take the matrix vector multiplication with our weight matrix w. If instead we multiply some constant c by our original input, the output that we'll get is going to be the original output from our first function call, just scaled by the constant c. And so this is useful to think about because in the context of image classification, this is a somewhat suspicious kind of aspect of our classifier, right? Because we could imagine taking our image and scaling it by some constant. That is potentially changing the semantic information that's in the image. Whereas our classifier is simply going to be changing the scores by a constant. So it's not going to have a chance to actually change maybe what category is being predicted if you're taking like the max score, for example, as the final prediction. So this is a result that's kind of important to think about, right? Because you can imagine how the semantics of your image really should be changing, and your predictions should be changing relative to one another as the input is scaled. So that's one way that we can think about it, right, in this algebraic viewpoint. An additional viewpoint that we can try to use to build some intuition is we can imagine this same math, like this same linear function being represented, but instead of taking a square weight matrix and multiplying it by our linear vector. Instead, what we could do is we could try to interpret what the rows of the weight matrix correspond to. Because if we think about it, these rows are essentially, we take the inner product of each row of the weight matrix with the column vector image to produce the score corresponding to that class. So so on the left-hand side of this figure, where my cursor is over here, if we take the inner product between this sort of beige row of the weight matrix with our input image vector, that is what produces the final score for the beige category, we'll say. So if instead of treating that row of the matrix as a row, and we then did the kind of inverse reshaping operation that we had done first to the image, we could try to interpret those parameters within our weight matrix as actually an image, as sort of a template pattern that the weight matrix is trying to match with the image. And so that will potentially let us interpret what our particular parameters are trying to use when they make their decisions for which score to give to each class for a given image. So to look at that in a little bit more detail, so these are the results that are from my implementation of a linear classifier, which you'll implement in project 1. And what I'm showing here, these are the templates that were learned by my model from this props data set that we'll be using for each of the categories. So in other words, each of these 2D images are really a row vector from a very large weight matrix that was learned by my linear model. And so what you can start to see if you sort of take a look at these images is they really are representing, from our human standpoint, some semantic information that could be useful for categorizing a particular image. So for example, if we focused on the mustard bottle, one thing that we can note is, first of all, this template is using the color information about the specific brand of mustard bottle that's in our data set, which you're probably familiar with. I think it's the Hellmann's brand, which is pretty typical in stores in this area. So it's using the color information about the mustard bottle. But in addition to that, it also is potentially trying to learn some information about how the pose of that mustard bottle is oriented in the images. And what I mean by that is that the blurring pattern within the mustard bottle is generally indicating it expects to see the mustard bottle kind of vertically oriented, sort of as you would see it in the store or on a table. But in addition, there's some blurring on the horizontal kind of axis of the image. And so that, to me, one interpretation that I try to take from that is that within this data set, the mustard bottle is not always positioned perfectly sitting on a table vertically upright. It can sometimes be oriented at an angle. It could be on its side. And so this blurring pattern, to me, is indicating that the model is trying to learn all of those modes of the data, but it can only use one template to try and represent all of those. So that's kind of one interesting way that we can try to interpret what our model is learning. It's also interesting to kind of go through some of these other ones. In particular, it's like this tomato soup can. It's Campbell's Soup Can is the brand. And so you can actually see it does capture, it's even to some extent trying to capture the Campbell's logo within the template. So for me, it's pretty fun once you actually get your models working to visualize some of this output, just because it looks quite cool. But it is useful for also understanding how the model is making the predictions that it's making. Okay, so that's one approach that we can use to sort of understand our models, right? So we looked at the algebraic approach first. We also looked then at sort of a visual viewpoint to try and understand our models. But there's also a geometric viewpoint. So because our models are linear functions, we can try and understand from the standpoint of geometry of that linear function space what the model is using to predict its output scores and how those scores will change based on the inputs. Right. So one way that we can think about this is as follows. So let's say, in this plot, what we're showing here is we've picked, let's say, one pixel. So let's say the pixel at the 15th column, the 8th row, and then the 0th color channel of our, let's say, image of the cracker box here. And what we're then showing, so that's the horizontal axis. It's just the value of the intensity of that one pixel as you increase it or decrease it. On the vertical axis, then, what we're showing is the classifier score and how the classifier score would change as the intensity of that pixel changes. And so because our function is producing, let's say, in this case, 3 scores to try and predict between these 3 different classes of either the sugar box, the cracker box, or a mug, the scores and how those scores relatively change is then shown within the 2D plot here. And so because our model is linear, each of those scores is going to vary as a linear function. So that's what we're showing. So the way then to interpret what particular category our overall model is predicting for a given pixel intensity value at that pixel is to just take the max score, let's say. So if the value of the pixel was where my cursor is here, sort of in the center of the plot, our model would predict that it's a cracker box. But if instead that pixel was shifted in intensity to a higher value, our model's overall prediction would change to be saying that the mug has the highest score. And so these linear models, we can think about them as essentially trying to cut up the overall high-dimensional pixel space that represents all the possible images with these planes, with these hyperplanes. And so this is what's referred to as the geometric viewpoint of trying to interpret your linear classifier. So it's kind of illustrating them what I was sort of describing a moment ago. Within this portion of the image space for pixel values taking on this range of values, our model would predict sugar. For this range, it would predict the cracker, and so forth. An additional sort of extension then of this viewpoint that we could use to try and interpret our models even further is if we extend, instead of one-dimensional, so just considering one pixel, we could imagine the full. Eventually we can imagine the full high-dimensional space of all the pixels, but instead let's move to like a two-dimensional space. So let's say we show that same pixel 1580 on the x-axis, and then we've picked another pixel, which is, let's say, somewhere here in the image in this lower right corner as the vertical axis. So once again, because our model is linear, there's going to be a linear basically plane that cuts through this pixel space, which corresponds to a level set of the score. For, in this case, with this red line, it's the mug. So in other words, any images that fall along this line for pixel intensities for these two pixels, the corresponding score from our model is going to be the same value, even as the pixels change intensity. And in contrast, what happens is if the image within this space is moving perpendicular to this level set, we can think about it as the score that our model is predicting is going to increase linearly. That's the result of our linear function. So in addition to that, one consequence of this kind of interpretation is that we can actually imagine and it's actually not even imagine, but it's just the fact that our mug template that our model learned, if we treated that as an image, it would exist along the line that is perpendicular to this level set of scores somewhere within pixel space. So we can think about that as being it would correspond to a very high score. If we normalize the image, it would be the maximum score, but that's probably more interpretation than we need. So yes, so we have this geometric interpretation. And once again, though, because our model is predicting a different score for every category, we could imagine that there's not just the scores for the mugs. We could add different planes within this space, which would correspond to the predictions to go along with each of the different categories that our model is expected to be trying to classify. And so overall, if instead of considering just these two pixels, it's hard to imagine, certainly for me, but if we imagine the high-dimensional space over the full image pixel space, the linear classifier, ultimately what it's doing is it's trying to set a set of hyperplanes within that high-dimensional space that would classify each region of space correctly. That's the goal. So in these low-dimensional, like one-dimensional pixel or two pixels, it's easy for us to kind of imagine in our heads. But beyond that, certainly for me, it's very hard to work with, to try and build some intuition about hyperplanes. So there is a limitation to what the geometric viewpoint can really give us. All right, so let me pause there and see any questions so far, or any questions so far? I'm gonna get a drink. How do we generate the templates? So that'll make a lot more sense in project one. So you'll be generating the templates. But essentially, I'll go back for a second to this slide. So the way that, or maybe this slide. So the way that the templates are generated is, let's just hypothetically say that we've trained a linear model to perform very well on this classification task. So let's say that we have a weight matrix here that is quite accurate at classifying the images that it's given. To generate the templates, all we're doing is we're taking the rows of that weight matrix and we're just reshaping them, each one, into a grid that is the same shape as the input image. And so that grid, if we were to flatten it into a vector and flatten the image into a vector, those two vectors inner product is what's producing the score in our classifier. So it's just a reshaping of our rows within the weight matrix to produce the templates. So linear classifiers, as we kind of saw based on those templates, it seems like they can learn useful information. And we'll find on project 1 for this props data set, like we can even get above 50% classification accuracy, the top 1 classification accuracy. The one downside, though, with linear classifiers is that they are limited to these linear hyperplanes for their classifications. So there are data sets for which it is impossible for a linear classifier to achieve 100% accuracy. So all of the cases shown on this slide, where the different regions of space, like the color for each region of space would correspond to the expected classification for any points within that region of space. So like this upper right quadrant, all data points within that portion of space should be classified red, and any portion within the upper left quadrant should be categorized as blue. It's impossible to actually try and draw out a hyperplane in this space that would correctly classify all of the points. And the same goes for the other two cases. So there are limitations built into our linear model, which in the future we're going to want to try and overcome. So we've looked then at sort of 3 different viewpoints that we could use to try and build some intuition on how our linear classifiers perform. So the first was an algebraic viewpoint, which just using linear algebra and concepts from linear algebra, we saw how we could manipulate the actual operations and what it's representing. From a visual viewpoint, we can try and interpret the templates as sort of a template matching operation that the classifier is using. And then finally, a geometric viewpoint where we try and imagine these hyperplanes in high-dimensional space and how the scores are being predicted based on those hyperplanes. So far we've defined just a parametric approach for producing this score, right? So we've just assumed that we have a weight matrix that is representative of some useful information, and that weight matrix, when we put it into this linear function f of x comma w, it'll produce good output. The downside, though, is that we haven't defined how it is we're going to choose that weight matrix, and it's not clear, intuitively at least, how it is we can go about finding a good weight matrix, right? So one question we should start to ask is how it is we can do that. So for the rest of today's lecture, we'll start to talk about loss functions and how we'll use loss functions to go about measuring what a good weight matrix is. And then in the future lectures next week, we're going to be looking at optimization as an approach to actually programmatically improve the weight matrices that we are starting with based on our choice of a loss function. All right, so what is a loss function? So a loss function ultimately is going to be a function to try and measure how good our current classifier is. So how good is our current parameters for classifying images. So a low loss would correspond to a good classifier. A high loss would correspond to a bad classifier. Sometimes you'll also see this referred to as an objective function or a cost function. Or in the case of reinforcement learning, usually it's called a reward function, a profit function. There's other names, but generally across all of these different names, or when you see them in papers, if they use other names, the goal of that function is ultimately to define how good is our current model, and it's what we're trying to improve during training. So kind of writing this down a little bit more concretely, how a loss function is actually computed is ultimately going to be based on the training data that we have. So let's say we have some given set of examples. So in this case, we have this set of images from 1 to n, so n total images, x, and each x has a corresponding label y. To define the loss for a single example from that set, what we'll do is we'll measure the output of our function, so f of x and w, and we'll compare it according to this function L with the label y sub I, so the corresponding label to the input image x sub I. So that gives us the loss for one example. If we then want to take the loss over the full data set to get a more representative measure of our model's performance, what we'll do is we'll average the total loss across all the examples within the data set. And so these kind of in all the projects moving forward, this is going to be at the high level the form of the loss functions that we'll be implementing. So it's the average over the individual example losses. So given that then, what we're going to look at for the rest of today's lecture are two specific losses which we'll use to actually start training our linear models. So the first loss is called the cross-entropy loss. And the goal, the sort of high-level goal, is we want to interpret the classifier scores that we're getting from our linear model as probabilities. And so that would then give our final decision-making system, which is using the output from our model, some way to judge what the scores really mean, right? And in this case, we'll interpret them as probabilities. So let's say, and I know I can't move my mouse. So let's say that we have this score function, s is equal to f of x sub I comma w. What we're going to use to define the probabilities from those scores is what's called the softmax function. So on the upper right-hand equation, this probability that the label is equal to some class k conditioned on the input x being equivalent to the input image x sub I is just the x function of the score for the particular class that we're interested in divided by the sum of x of all of the class's scores. So that is just like a normalization of the x function evaluated on all of the classes. So let's look at what that looks like with an actual concrete example to make better understanding of the Greek. So let's say that we have our Cheez-It box image, and let's say that the scores that are produced by our linear model are given as the numbers for each of these three classes. So let's say Cracker has a score of 3.2, Mug has a score of 5.1, and Sugar has a score of negative 1.7. So this is just the raw output from our linear model. These are usually called logits or unnormalized log probabilities in the case of a cross-entropy loss. So the first step to generate the probabilities that we want to use to interpret the output is to take the x function of each of these values. So at this point, what we have are unnormalized probabilities. So what this x function is doing is it's ensuring that all the score values are no longer negative. So at this point, we can start to treat them as unnormalized probabilities because we don't have any negative values. At that point, then, what we'll do is we'll normalize. So we'll take the sum over each of over all of those unnormalized probabilities, and then divide each of them by that total sum to produce our final probability list, which is in the green column. And so in this case now, we've guaranteed that the probability is summed to 1 by the final normalization step. So this is just the process for defining how it is we're going to convert from the raw scores into something we can call a probability. So it's a way to just interpret the raw scores as a probability. At that point then, what we have is the cross-entropy loss function, where we'll take the loss for this particular example is going to be defined as the negative log of the probability for the correct class conditioned on the image. So in this case, the correct class is the Cracker box. So what we'll do is we'll define the loss sub I. So the loss for this example is going to be the negative log of that probability, which in this case is 0.13. And so this is referred to, using this loss function here would be referred to as an example of maximum likelihood estimation. So we're not going to go into the theoretical details of maximum likelihood estimation. It's a broad approach within machine learning to use to train your models. So if you're interested in more of theoretical details, EECS 445 or 545 will spend a substantial amount of the course focused on this topic. But for our purposes, the idea is that by choosing this loss function, what we're essentially trying to do is we're trying to say that we want our model to predict the highest probability on the correct class. So in this case, we want the model to produce the highest probability on the Cracker class. That's the goal of this loss function. So in addition to that, one other interpretation that is sort of interesting that results from this choice of loss function is a connection to information theory. So again, this is probably not something that we're going to need for our projects or moving forward with our, once we go towards the research side of things on the robotics side, but it's an interesting result that you can actually show. So there's a measure of difference between probability distributions called the Kullback-Leibler divergence, which is used commonly in information theory. And it turns out that you can show that the cross-entropy loss, which is the H function, is actually related to the Kullback-Leibler divergence. If you want to go into more details, we can talk at office hours about that. It's just sort of an interesting result that is produced by this choice of loss function. Okay, so putting this kind of in kind of restating what we just went through. So the goal of the cross-entropy loss function is to maximize the probability of the correct class. So in that black box, that's the loss function for a single example that we would have within our training set. And if you then substitute in the term for how our probability is extracted from the raw scores, you get then the box that's shown on the right. So when you go to implement the cross-entropy loss in Project 1, that's the box that you should look for. Okay. So a couple questions. So at this point, I think what'll be good is to turn to the partner next to you, to either one of your sides, and I've got a few questions here that are kind of interesting to go over, and just talk amongst yourself for a few moments, and then we'll come back together to see if we can answer it. These first few should go kind of quickly, so I'll probably just give maybe 2 minutes or so. Just introduce yourselves. This is a good way to also maybe start forming teams type of a thing, and see if you can answer. So the first question is, for this cross-entropy loss that's defined, what would be the minimum possible and the maximum possible values for this term? So we'll come back together at 350, let's say 356. And if you're online, you can feel free to talk in the chat. All right. So let's bring it back together here. So it sounds like people have had some good discussions. So let's see. So does anyone want to sort of take a guess here at the answer for what the minimum possible value for this loss would be, and the max? We could do both of them. Any thoughts? Yeah. Minus infinity and 0. Yeah, that's right. So I mean, depending on how you want to define with the negative sign, yeah. But yes, you're right. So the minimum value here would be 0 if you get the the correct, the highest, predicting a probability of 1 on the correct class, and then you could potentially have infinity if you predict a 0 on the correct class. Yeah, so nice job. So because of time, we'll probably go. I've got a few more of these questions. We'll probably do a couple more of them in these kind of breakaways types of discussions. But for the sake of time, so let's consider the fact that if all the scores are small random values, what would the loss be? Asking these kinds of questions is actually a really good debugging approach, sort of a sanity check when you go about implementing these loss functions, because you can actually test your implementations with random inputs to make sure that you're getting roughly what you would expect. So in this case, if you have random scores, you would expect then your probabilities to be random, and correspondingly, you could estimate then that the loss for an average prediction would be negative log of 1 over the total number of classes, right? So that'd be a random probability, and in this case, that comes out to 2.3 if we have 10 classes. So on Project 1, actually, this is a check that's built into the notebook files that we'll be using. So it's a really good sanity check just to make sure that your implementation is performing how you expect. Okay, so that's the first loss function that we'll use to train a linear classifier. Another one that we're going to be talking about for the rest of today's lecture is what's referred to as the multi-class SVM loss. And so this loss function places a different set of priorities on our weight matrix that we're going to want to be training. And so instead of working with probabilities and trying to reason about which weight matrix is better than the other weight matrices based on the probabilities that they would produce as output, this one has the interpretation of trying to simply say that the score of the correct class should be higher than the scores produced for any of the other classes on a given input image. And so visually, one way that we can interpret that is in this plot that's shown here. So sometimes these types of losses, when you see these plots, are referred to as a hinge loss just because of the shape looks like a sort of a door on a hinge. But the way to interpret this is it's saying that on the x-axis, what we're showing is the score for the particular correct class of this, let's say, input example. The vertical gray line that's pointed to as the highest score among the other classes is, as that title suggests, it's for all of the incorrect classes, what was the max score produced by the model. And then the distance between that max score for the other classes and then where the loss goes to 0, that's referred to as the margin. So what this multi-class SVM loss is essentially incentivizing our parameters to do is to ensure that the score for the correct class is beyond the margin away from the next highest score. So it's trying to ensure that the score for the correct class is the highest score produced and is higher than all of the incorrect classes' scores by at least that margin distance in the dimension of the score output. And then if the score for the correct class is not beyond that margin amount, higher than the next highest score, then the loss simply increases linearly with the difference between those scores. So writing that out mathematically, here's the approach that we'll use for actually implementing this loss function. So let's say that we're given an example image. So we have x sub I and y sub I. Our scores then are once again defined as s being equal to the output of this function f. So the SVM loss then is the third equation on the right-hand side of the slide. So the loss for this particular example I is going to be the sum over all of the incorrect classes. So our sum is over all of the categories where j does not equal to the correct class y sub I. And then we're taking the max between either 0, if we're beyond the margin, but 0 or the difference between the incorrect score and the correct score plus 1, where in this case, the value of 1 is chosen as our margin. So this is then the equation that we'll be implementing when we go to implement the multi-class SVM loss for project 1. Let's work through an example to sort of build some intuition about the notation in this slide. So let's say that we have 3 example images, and then each image obviously has a corresponding label. So on the left column, that's the cracker box that we've been talking with. The middle column is going to be an image, and then the corresponding scores produced for a mug from our data set. And then the third column is a sugar box, and then the scores produced by our model for the sugar box. So if we were to work through how we would calculate this loss, it's shown on this slide. So the first thing we would do, so for the cracker box, so I'll walk through the math that's shown on the red text on the right-hand side. So what we would do is, so the first thing we're doing is we're summing over all the incorrect classes. So this j does not equal to y sub I. So that means we're going to go over the mug score and the sugar score, because the input image in this case is the cracker box. So for the mug score, what we're doing is we're going to take the max between 0 and then the mug's prediction score of 5.1 minus the correct prediction, which is this s sub y I, which is 3.2. And then because that difference plus 1 is greater than 0, that is going to contribute some loss to our overall term of 2.9. So the way to interpret that means that the incorrect class mug had a higher score prediction than the correct class cracker, so it's contributing some loss. It's indicating that our model is not performing well because it's not predicting the highest score for the correct class. In contrast, though, the second term within the summation, which is for the sugar box, that contributes ultimately 0, makes 0 contribution to the overall loss, and that's because the cracker score was above the margin away from the sugar box score. So working through these examples, I think, is a good exercise on these small kind of examples because it can be sometimes difficult to connect the math notation to the actual code that you'll be working with in the tensors. So on the second example, it turns out that the mug score of 4.9 is greater than the incorrect category scores, so the cracker being 1.3 and the sugar being 2.0. And not only is it greater than that score, than those scores, but it's greater than those scores by more than the margin. So overall, the loss for that second example, the mug image, would be 0 because it was correct, and it was correct by more than the margin. The third example then shows a very, very large loss, right, of 12.9. And the way to interpret that is it's because the sugar box, which is the correct category, had the lowest score, and by quite a bit, compared to the incorrect categories. So if you work through the math, you'll get to the same answer. Okay, so given then that we've calculated the loss for each of those individual examples, then what we would do is we would sum that loss and divide by the total number of examples in our data set. In this case, it was 3 examples to produce the overall loss of our model on the data set. Yeah, question? Yeah, so there are alternative versions of the SVM loss. Any change you make to the SVM loss, actually we have a couple questions on this, will potentially change what your parameter, like what the final parameters of your like optimized model are. So in some sense, what you'd be doing is you'd be saying like you have a preference for models that actually are producing probabilities over these models that are like not producing any output that we would want to interpret as a probability, but just producing highest output by this fixed value for the correct class. So you could make alternative loss functions that do that. But what you're essentially doing when you pick any loss function is you're choosing how you want to prioritize certain parameter choices over others. And so the resulting performance that you'd expect to see will be affected by your choice of loss function. We would have to test it. It's hard for me to reason about how, it's like very difficult to reason about those like high dimensional input spaces with like these large models. So we'd have to test it. It'd be a good experiment to run on project 1. Okay, so a few questions, so there's actually like a number of questions. Oh yeah, another one. Yeah, so if you remember in lecture 2, we talked about hyperparameters. So like in k-nearest neighbors, like the choice of how many neighbors, the k was a hyperparameter. The choice of loss function, it turns out, is also a hyperparameter. So you as a human, like you're choosing a loss function to use without thinking about the data. So you're not learning the loss function from the data the same way you're going to be learning or your algorithm is going to be learning the parameters of the weight matrix from the data. So as a result, the choice of loss function we would call a hyperparameter. And there's different, there's not like a standard gold rule for how you would pick a loss function. To some extent, it'll depend on what your input and output data is, because some loss functions, for example, like this loss function is defined for an input of an image and an output of a discrete label as opposed to a continuous label. So to some extent, your problem space constrains what loss functions you can use, but otherwise you essentially have to try many loss functions potentially and see which of them produces the best, most accurate model on your test data set. Yeah. Okay, great questions. So, so a couple questions to think about. I think for time, I might kind of go through, kind of step through these. So the first one, so one thing to sort of introspect and see how we're understanding this. So let's consider what happens to the loss if the scores for the mug image, so that middle column, if they were to change just slightly. What would happen to the overall loss? And the answer is, in this case, we would not expect the loss to change because the mug scores are, first of all, the mug is the correct class, right? It's the correct category. And the score that was produced of 4.9 is substantially larger than the margin of 1 from the incorrect scores that were produced. So as a result, if we were to just slightly change that mug score to like 4.8 or 5.0, we wouldn't expect the loss to actually change. Another question that we could ask, so what are the minimum and maximum possible values of this loss? Right, so in this case, the minimum loss would be 0. And as we saw in the case of the mug, right, where it produced a very high score on the correct class. And the maximum possible loss in this case would be positive infinity. So another question, and this is an interesting one to think about. So let's do another like breakaway, kind of talk to those sitting next to you again. Let's consider, what if all of the scores were random? And so to ground that a little bit more, let's say that all the scores produced by our initial model are random in the sense that they're centered on zero mean Gaussian distribution with pick any arbitrary variance that you'd like. Let's consider what would the resulting loss be for a model that produced Gaussian random scores. So we'll take 2 minutes. So we'll come back at like 4:10 and see what people think about. This is a fun one to think about, I think. So what do you think? What if all the scores were zero mean Gaussian? Yeah, so one way to think about it, so like let's say, so on average, right, like if we have like a zero mean Gaussian, that means like on average, you randomly pick a score, it would on average be zero, right? So like let's ask the question, like if on average that's zero, that's zero, then it would on average cancel each other out, right? So it'd be 1, at least for those two, right? So let's say that like for the cracker box, it's 1. And like so let's say we're trying to predict the mug as the cracker category. So the mug versus cracker cancels out to 1, and then the mug versus the sugar, which would be the second term that we have to do in our score also makes sense. So that would also cancel out because there's 0 1. The number of classes minus 2, right? Because we ignore the correct maps. All right, so let's come back together, and so let's see. So do we have a volunteer of who wants to try and like venture a guess or walk through how they and their partners sort of looked at this problem? Any volunteers? It's okay to take a guess too and not have an explanation. Yeah. 1. Okay. So what's your thinking behind 1? Yeah. So does everyone see the reasoning there? So it's not 100% correct, but the reasoning is totally solid. So if on average the scores are centered on 0, then on expectation, S sub j and S sub y or S sub y sub I are both gonna once again on average be 0. So they'll cancel out. So you're left then, at least on this one example, with a max of 0 and 1, so you get 1. All right. So we're really close, but we're missing one little piece. Well, I think that the reasoning about the expectation is still true because because we're saying like all the scores are random with 0 mean on average. So like so whether it's S sub j or S sub y sub I, we can treat them as both as on average as being 0. Let's see, we've got a bunch of hands up. Let's see, over here. Right. Yep. Exactly. So putting those two reasonings together, you get the right answer. So if we just remember that we have to do that outer summation over the incorrect categories, then because each of those terms within the summation is 1, as we got from the reasoning about the on average cancel out of S sub j and S sub y sub I, the summation then of n minus 1 terms is going to get a n minus 1 total. Nice job. So I have a few other questions here in the slides. So let's see. So because of time, I'm going to flip through these. I would recommend kind of thinking about these. They're on the slides up online, kind of at home. And then if you're interested at office hours, we can go into more, we can kind of discuss them. But let's kind of move on. I've got even more questions. Let's see. So let's compare now the cross entropy loss that we looked at the start of lecture versus this SVM loss that we looked at towards the second half of lecture. So once again, the cross entropy loss is on the left-hand side, so you'll implement that for project 1, and also the SVM loss that we deduced is also on the right-hand side of the slide, which you'll also implement for project 1. So let's assume that we have these set of scores then shown on the left-hand side, and we want to try and compare and like contrast these two losses together. So in this particular case, what we're showing is like three separate examples. So just for the sake of time, so let's kind of step through these. So the first one, so if we were to ask what the cross entropy loss is, so if you work this out, it's going to be greater than 0. Like working through the exponent functions is kind of hard to do in your head, but if you work it out, like that'll end up being greater than 0. But the SVM loss, because the correct category, which is the ones highlighted in green, are all producing scores greater than the margin of 1 away from the other incorrect categories, that SVM loss is going to be 0 because they're all correct and they're all greater than the margin. Another question that we could ask is like, what happens to each loss if you were to slightly change the scores of the final data point within these three predictions? And so in that case, the cross entropy loss is going to change because like the normalization term, one way to kind of think about it is that normalization term is going to make your final loss depend on all the values of your scores. Whereas for the SVM loss, so you're right. Actually, if we did change, so if we change the scores of all the data points, which is how I was interpreting the question at first, the SVM loss would change for that second row, but for the first and the third rows, and where the third row is the final data point, as the question asks, the SVM loss will stay the same because of the margin. But yeah, good catch. Yeah. Let's see. All right. So back to this one. So what happens to each loss if I double the score of the correct class from 10 to 20? So for the cross entropy loss, if you work through it, it'll decrease, but the SVM loss, by kind of similar reasoning about the margin, will stay at 0. Okay, so to recap, because we're running out of time here, so we looked at 3 different viewpoints that we could use to sort of interpret our linear classifiers that we're going to be building in project 1, from the algebraic viewpoint to the visual viewpoint, where we had those templates and treated the overall linear function as a template matching operation, up to the geometric viewpoint with hyperplanes in this high-dimensional image space. We looked at 2 different loss functions, and the key idea with the loss function is we're trying to quantify some preference over the potential parameters that our linear classifier has. So we looked at the softmax loss function shown on this slide, and also the SVM loss function. And both of these are going to be implemented in project 1. The one thing, though, that we have left out, if we're actually going to produce a linear classifier that can perform well, is how we can find the best possible setting for our parameters, which is the weight matrix and the bias vector. And so in the next lecture, we're going to be looking at regularization and optimization, which are the approaches that are actually going to allow us to improve the weight matrix from some initial guess, so that our models actually perform well. And so with that, that's the end of today's lecture. Thanks for coming out. If there's any questions, I'll stick around, and thanks.